Limits with direct substitution. If I have a continuous function, such as parabola right here, I can simply put in the value of the limit I'm looking for right into the equation. I got an equation here, f of x equals 6x squared plus 5x minus 1, just a parabola. And if I put in -1 right here for the limit, I don't have any holes, I don't have any discontinuities, I don't have any piecewise functions. I'm just going to put it right in. I'm going to use the equation. Here's x squared, and if x approaches -1, -1 squared is 1. 6 times 1 is 6. Now I put x here, -1. 5 times -1 is -5, and I still have -1 left over. 6 minus 5 minus 1 is 0. And when I put in right here, -1 for my x, you can see it lands right on 0. Let's suppose I put in 0 for my limit. Limit f of x is x approaches 0. I put in 0 for the x. 0 squared is still 0 times 6. 5 times 0 is 0. All left is -1, so my answer is -1. And I look at the graph right here. When I have 0, it ends up at -1. Another example, this is a cubic function right here, referring to the cube right here, which is the highest degree. F of x equals 2x cubed minus 4x minus 3. As x approaches 2, I'm going to put in 2 for the x cubed. 2 cubed is 8 times 2 is 16. Minus 4 times 2 squared is 8. -4 times 4 is 16. And then minus 3 at the end of the equation. These two cancel out. My answer is -3. So x approaches 2. Here's 2 right here. F of x is approaching -3. I put in 0. 2 times 0 cubed is 0. -4 times 0 squared is 0. And I'm left -3, and I've got another -3. And I put 0 here for the x. My f of x is also 0. X approaching -1. I put in -1 cubed. -1 times -1 times -1 leaves me -1 times 2 is -2. Minus 4 times 1 squared. -1 squared is 1, but minus 4. I'm multiplying it by, so -2 minus 4 and then -3. -2 minus 4 minus 3 is -9. And when I go to -1 right here, I am at right here, -9. Now I'm looking at some substitution here, direct substitution of different types of trigonometric functions. Now what I'm looking at here is, what do you call it? Unit circle, excuse me. And the unit circle here is defined as a unit of 1 is the radius no matter where I go. And these are the coordinates right here. Now, what I want to understand is on the unit circle, in addition to being coordinates of x and y, such as at 0 degrees, right here, it's also that 0 degrees at 1, 0. That's also the cosine and the sine. And I want you to understand here, most importantly, as I got an equation here, sine x, or f of x equals x over sine x. Now, if I have sine x here and x is 0, it's undefined. That would put a 0 in the denominator. I can have a 0 in the numerator, but I can't have a 0 in the denominator. If I graph this, and it looks like this graph right here, it's kind of a strange looking graph. I got an open hole here, and if you put this on decimals, this is undefined, obviously, because I can't have a 0 in the denominator. This sine x is 0, and I cannot have a 0 in the denominator. But it's approaching 1 from the left. It's approaching 1 from the right here. That's why it's approaching 1, 1 minus, 1 plus, approaching 1 from the right. And also, it's actually approaching 1 from both sides. So while I cannot equal it, it can approach 1 from all three sides. Another area we're going to look at, especially in the coming weeks as we explore more deeply in the calculus of differentiation, which we're using limits to get to that point, we're going to talk about E. E is a very advanced function, but it's actually pretty simple. Used a lot in financial interest rates, radioactivity, growth and decay of epidemics, as well as microbiology, and in mortality rates and in birth rates as well. The basis of this is, I'm going to start this first graph here. If I have an equation y equals 1 to the x, no matter what I put in for x, I could put in 1, 5, 10. 1 to the 5 is 1. 1 to the 20 is 1. 1 to the negative 10 is 1. I get this flat line right here. Let's make it a little more interesting. What if I graph this? Instead of y equals 1 to the x, I have y to the 1 plus 1 over x. And what's interesting, as my x gets bigger, this number gets smaller. In other words, if x equals 1, well, 1 plus 1 over 1 equals 1. And that's equal to 2. So x is 1 right here, y equals 2. But look, as our number gets bigger, as my x, let's suppose I put 5 for x, 1 plus 1 over 5 equals 1.2, or 1 1/5. Well, if I go to 5 here, that's not right there. So as my x gets bigger with this equation, my f of x gets lower and lower to 1. But notice, we basically got a limit here. I got an asymptote. It's never going to approach 1. It's infinitely close. I could put in a million for x. It'd still be 1 plus 1 over 1 million, which is 1.0000006 zeros plus 1. It still wouldn't reach it. Now, what makes it really interesting is I take my original equation, y equals 1 plus 1 over x to the x. And that's what this graph looks like. So, granted, my x gets closer and closer to 1. As it gets bigger, it gets closer and closer to 1. But then I'm putting it to a power here. And this is what we're looking at here. I've got an asymptote. This is where when my x, whatever my x is, my f of x or my y gets closer and closer to 2.718. It never reaches it. This is called E. It's an irrational number like pi, where pi goes 3.141529, and it never ends. It gets closer and closer. Same thing with E. And notice it gets flatter and flatter. It's almost approaching a slope of 0, and that's going to be used in the coming weeks. I put some numbers here. If I put in 1 plus 1 to the n over n, and n is 1, I get 2 for the result. I put 2, I get 1 plus 1 half to the 1 half, that's 2.25. I get bigger and bigger here. As my number gets bigger, let's suppose I put in 100,000, that's 1 plus 1 over 100,000 to the 100,000th power. Notice this, it keeps growing slightly, 2.5, 2.70, 2.71, 2.718, 2.718. It basically does not get bigger than 2.718. It infinitely gets closer and closer, but it will never reach 2.719. And again, this is E. And what we're looking at here is interest rates, where I got a base right here that's being added to over time, and then that same time is to the power. While this gets tinier, this gets bigger, but it's getting closer and closer to 2.178. Again, that is E. And like I said, we use it in investments and banking, probability theory, to see what outcomes are, even in gambling, looking like this, and where a lot of it was invented originally. Radioactive half-lives, quantum physics, epidemiology, as well as mortality and birth rates. Now, we're going to go from here. When we look at E, I'm going to look at logarithmic functions. Give you a review, logarithmic function. We use logarithmic functions when we cannot easily chart something from, let's say, 1 to 10 to 100 to 1,000 to 10,000 to 1,000,000. very impossible to have a chart that goes from 1 to a million that we can easily use. So we use logarithmic functions. The base of a log, suppose I have 9 cubed equals to, that's not 243, it's 729. Sorry about that. 9 cubed is 729. If I'm going to write it as a logarithmic function, it would be, here's my base is 9, it's log base 9, the answer, 729, and then my exponent is right here. Let's do another one here because I made a mess of this first one here, and this is much, the second and third one are correct. 2 to the 6th is 64. 2 times 2 is 4, times 2 is 8, times 2 is 32, times 2 is 64. Base 2, so it's log base 2. My answer is 64, I'll put right here. And the exponent to that base 2 is 6. 10 to the 4th is our scientific notation. And there's 4 zeros there, as you know, so I have 10 to the 4th. Well, that would be base 10, log base 10, 10,000, and the exponent is 4. Now, as I said in the previous couple of slides, 2.71827, it never ends, it gets closer and closer, and everybody increases, is E. If I have 2.71827, so on and so forth, the X, that's E to the X. Just like 9 to the 3, this is E to the X. But we don't write it. And if we have to do a logarithmic function, log E to the X, we write as ln X, and that stands for log naturel, which is French for actually natural log. If I have E to the X equals 7.5, that means X would equal 2.0419, and I just use a calculator for that. But let's look at this. How do I write this? It's base E, base 2.71827. That's our E. 2, I got an answer. My X is 2.0149. And then the power is 7.4999. That's kind of long complicated. I'm just writing it instead of log E 7.5 equals 2.0419. I'm going to write it ln 7.5 equals 2.0419. E to the 10 equals 22,500. I would simply write, instead of log E 22,500 equals 10, I'm going to write ln 22,500 equals 10. Now, let's look at some undefined limits with direct substitution for the natural log. I've got an equation here. X over ln x. Now, it's undefined at x equals 1. Why? Look at my ln x, my upper graph right here. At x equals 1, my f of x is 0. So guess what? I cannot have a 0 in the denominator, that's what this would put right here. And be 1 over 0. But it is a limit. I can approach it from both sides. It's approaching as x approaches 1 from both sides, f of x approaching 0. From the left side, from the right side, from both sides. So I can do a limit with this. And then the other thing I want you to notice here, let's look at 1. X approaches 1. It cannot be 0. Why? I've got a vertical asymptote right here. This is that x over ln x. This is the original log, natural log. This is x over ln x. I can't be 1 because that gives me the 0 we were talking about. But it's approaching from both sides right here. It's approaching from the left. Let me make the arrow here. From the left, it's approaching negative infinity. That's what I got right here. No matter, as I get closer and closer to 1 from the left, it's approaching negative infinity. As I'm approaching from the right here, it's approaching positive infinity. We'll be using more of this in the coming weeks. I want you to just get a basic understanding of what the natural log is, as well as looking at trigonometric functions.